Can you hear me? Can you hear me now? All right. I have to set my timer because otherwise I guess I will be talking for way too long. I joked yesterday already that in order to prepare a 6-hour talk, I only need 40 minutes. But in order to prepare a 40 minutes talk, I probably need 6 hours. And I only spent 5 hours yesterday night. So, well, it's just 60 slides, but I guess we're going to get through with that.
Oh, the beamer is on. Beamer is turned on.
Yeah. Of course. Did you?
Oh, that was my fault.
Well, the moderator threw a microphone on the on-off button.
That's right.
Well, at least if I'm talking too long now, I can just say, well, it was all the projector.
When it's blinking, is that turning on?
Yeah, it's turning on, but well, all right. I guess I can go without the slides in the first place. So, I guess a lot of you guys are software people. Who of you has actually done hardware with their own hands? All right, that's good. Okay, and who of you has ever done hardware with your own hands and thought, oh, damn it, I'm so stupid? Yeah, that's good. All right, so nothing that I'm going to talk about in this presentation should be taken too seriously because obviously I'm a moron and I screw up constantly. And if anybody sees this, it's on. Yeah, it's coming. So if anybody sees that presentation who actually knows what they're doing when they have a wire bonder, I'm very sorry if I offend you with my presentation. All right, so before I get into it, I want to put a different hat on, the host organizer hat, and I want to thank you all very much for being so wonderful guests coming to Bochum the second year in a row. And I want to advertise our nonprofit that runs those shows in Bochum, the EMBO conference and the Kicon and the Open Tapeout conference and the Practical Data Science conference and stuff like that. And if you are interested in being up to date, please join our newsletter and help us connect engineers and universities and run conferences. All right. I would say connecting this thing to the thing on the left to one of the things on the right is easy. Yeah, I guess we can all agree. How about that? Still easy, right? We look at that. Okay, it gets a little bit harder. And we look at that. Okay, gets a little bit harder. Well, this depends on how much experience you got. It can be quite easy. It can be quite hard. I don't think I have to say anything about hand soldering those little thingies that always breaks me. But who of you has tried connecting this to a PCB? Like who? All right. Oh, so a few. That's good. That's good. Maybe you can tell me after this talk what I'm doing right or wrong. So what you can see there is a tiny silicon chip. Not 2 millimeters. Sorry, it should say 2 centimeters, but I'm stupid. All right, it doesn't have a few connections. It actually has a couple of connections that need to be made. And, the pads that we need to use for that are not that wide, actually. So a pad on one of those chips that I just showed you has approximately 80 microns of width, and the pitch between those is 100 microns. So what I figured out when I started working with silicon chips is that positioning something under a microscope with an accuracy of about 5 500 micron, 250 micron is still possible if you have really, really steady hands. But at 100 microns, you're absolutely lost. You need a machine to do that, because otherwise you will just screw up. So what we usually do when we want to connect those chips to our PCBs is a process called wire bonding. Wire bonding, I put a lot of text on this slide just to make it super, I don't know, look as if I'm doing something really crazy. Well, it's basically a solid state welding process in which we attach a wire to the metallized layer of our silicon chip or to the surface finish of our PCB. Pierre already talked about that this morning when he said, oh, okay, when you want to bond a chip directly to the PCB, you should use INIC, right? I don't know for how many people that is actually necessary, but what we're using there is ultrasonic energy. So in over the next couple of slides, I want to run you through the process of what actually happens when you wire bond a chip to a PCB. Because I can tell you, yeah, we push that down and then there is a little bit of ultrasonic vibration and it gets stuck. That's done, right? What do we need to do that? Well, we need a wire bonder. A wire bonder, as you can see here, is, well, basically not that much different from a really fancy 3D printer, right? It's a standard CNC tool. You've got an arm that's moving around over a stage. You can lower it and raise it, and there is a CNC computer in it. It runs some sort of G code. But additionally to that, well, no. So it has a wire feed, so basically also the same thing as a 3D printer where you have like a filament feed, and you have a stage that you're working on. But in addition to that, you will probably need some form of a clean room or at least a clean room. So if you're going to get one of those machines, you don't want to have too much dust in them. That usually screws up your working quality. The machine that you're seeing here, that is a very, very tiny machine. It's not the smallest, but it's also not one of the biggest. You can get one of these for already 150K, which is not too bad, actually. I mean, when you dial the time back like 20 years, those things were way more expensive. And but there's one thing that is not on here, and that is the actual bond tool, the bond head, the thing that does the actual work for us of connecting the wire to the chip. So since this is not a very good picture for it, I went into my laboratory this morning and took 2 pictures with my phone. And what you can see there is the actual bond head. So as I told you, right, it's a tool hanging from the top, same way as you would know it from a 3D printer. And then you have this tool. This tool is basically made up of 3 parts. One is the wire feed. The wire that I'm using in this picture has a diameter of 25 microns. So it's quite hard to push or pull that. So the difference to a 3D printer in that situation is that the wire is guided just by an airstream through a pipe. So there is a pipe going all the way around, same as a 3D printer, but we're not pulling or pushing the wire. We're just using a tiny air pump that is pushing it through. Then you can see the so-called clamp. The clamp is a tool that opens, goes back, closes, pushes forward, opens, goes back. So this is the only part of the bonder that is actually pulling or pushing the wire. I just said that the airstream is moving the wire through the feeder. Well, that's not completely correct. Let's say it helps the wire running through the actual tube, right? And then the clamp pulls it. It pushes it into the so-called wedge, or into the capillary of the wedge. This is a cross-section of a wedge. So the tiniest thing you see on the bottom, like the really tiny pointy part, that is the wedge. And as you can see, the wire is guided from the top right corner into the wedge, then pushed underneath the wedge. And when we're bonding with that, we can see in the bottom picture that the wire is guided through it and then pushed by the wedge onto the chip, or pushed onto the electrode, and in between that we see the actual bonding wire. So bonding is a super easy process, and it only has 9 steps that we need to consider. And in all of those 9 steps, well, a few things can go wrong. I'm going to talk about that later, but let's just start with the first steps. So the first thing is the initial contact. Well, chips are sensitive, and 25 micron wire is also sensitive. So the initial contact is actually a really critical phase of the whole bonding process. If you look at the machine when you're working with it, well, okay, it goes down and then at some point it starts working, right? But in order to create a good bond between the chip and the wire, the height of the chip has to be measured like really exactly. I think it's somewhere between. I talked to one of the technicians of that machine that I'm using just the other week, and I said, and I think they said they can reposition the wedge at 75 nanometers repetitive accuracy. So that's quite good, right? So the wedge is coming down, and until the wire meets the chip. And with a force sensor in the bond tool, the machine knows, okay, I just touched the chip, and then it applies a little bit of pressure to make sure that, I should have told you, first, I'm gluing the chip to my PCB, right? I'm not just laying it flat on the PCB. So I glue the chip on the PCB. The head comes down, pushes the wire onto the chip, and if you don't glue it correctly, if it's not glued at all, well, it might tilt, right? So there is a little bit of an adjustment that the bond head does to make an initial connection between the wire, the wedge, and our chip or our electrode. The second step that then happens is the so-called scrubbing. Scrubbing is the process of initiating those ultrasonic vibrations in the wire. Those wires, where I'm using aluminum wire here, well, it's easy to deform plastically, right? So it gets pushed onto the chip, and then the wedge starts wiggling from left to right, basically scratching the wire on the surface of the metallized layer of that chip. While doing that, it scratches off oxides. Yes, you do clean the chip before you work on it. But even after cleaning it doesn't take too much time until the uppermost layer oxidizes, right? And it only takes like a few oxygen atoms in that metallized layer to let your connection become brittle over time. So you want to push all of those you want to push all of those oxygen atoms to the side. Right, so the wedge comes, pushes the wire down, starts scrubbing until the power that is needed to drive the ultrasonic vibration decreases. Right, so it pushes down. It gets the wire is pushed onto a crystalline oxidized layer. It scratches the oxidized layer off, and at some point, the power that is needed to wiggle the wire becomes less. Right, everybody has probably had some experience like that. Well, not with the wire bonder necessarily. But that initiates the next stage, the next phase, right? So the next phase is a so-called deformation phase. In the deformation phase, the wedge really pushes the wire down and deforms the former circular wire into a flat bond, because we want to have, if we want to have a good connection, we want to have a large cross-section. We don't necessarily want to have only a large cross-section, but we want to have a well-defined ratio between cross-section that is connected to the chip and cross-section that is left, that our wire is still attached to the bonding point. Because if we just push it down completely, well, we can make a flat pancake, but then the wire isn't attached to our bond anymore, and that doesn't serve the purpose that much. You can see that. Well, you can see in the picture that a part of the wire is still attached on the left side, right? So I'm only telling you about one very specific type of bonding here. There are plenty of different types, and if you go in detail enough, you will find like 15 or 16 different types, different processes to bond a wire to a chip. Another process that is commonly used is ball bonding or thermo-activated ball bonding. Right, you have there you don't have this wedge where you just push the wire down, but the wire comes from the top, then gets activated, usually with with an inductive heater or something. It forms a ball, and then the ball is pressed down. There are plenty of different types, but this is now the wedge wire bonding. So the wire flattens, enlarging the contact area gradually, while still applying ultrasonic power. And the amount that you press the wire down, well, that is a very, very well-defined property of your process that you want to usually repeat. I'm going to show you some pictures in the end where you can see that I'm not really good at repeating that. But if you're good at it, I think you can repeat it quite well. All right, this deformation is now just a mechanical plastic process. But we don't want it to only geometrically attach to the surface. We actually want to achieve atomic bonding. We want to achieve interdiffusion. So even after the deformation is done, so our wedge pushed down the wire, and now we're still applying some ultrasonic power to, let's say, massage some of the atoms into the metallized layer and have them diffuse into one another to prepare everything for the next phase, the so-called intermetallic compounding phase. On the bottom picture that you can see here, you see, well, sort of an illustration of how well this atomic bonding depends on, for example, the ultrasonic activation frequency. So higher frequencies usually, well, I shouldn't say that higher frequencies, because at some point the frequency is too high to really bond it, right? But the frequency makes a difference. Let's put it that way. So this intermetallic compound phase, I did put it into the bonding phases here, actually, which is not completely correct, because this phase doesn't stop when the bond wedge lifts again from the chip. This intermetallic compound, well, it grows over time. It grows over time. So some chips are even cured after bonding. And what you can see here on the right side is a artificially aged chip. It was aged at 200 degrees, so that you can see the intermetallic layer growing. And on the top picture, okay, it's. I'm going to explain to you a little bit what you should see. Okay, so on the top picture you see a copper and a silicon. A copper and a silicon side, and there's aluminum on it. And if you look really, really closely, you can see some of the intermetallic compound already here. Then over time, this is after 4 days at 200 degrees. After 4 days, 200 degrees, this intermetallic compound layer already grew to almost 1 micrometer, and then over time it ages, right? And as I said before, while doing the scrubbing, we want to push out the oxide, because that would also make our intermetallic compound brittle over time. It gets brittle over time anyways, because the atoms don't stop diffusing. But having oxygen in it is not necessarily a thing we want to have. All right, so after performing the bond, and after the atomic bonding and the interdiffusion happened, we're not just taking the wedge and going away. We keep some of the pressure for some time, and we switch off the ultrasonic power, or reduce the ultrasonic power at least a little bit, to temper or cure the bond pad. So we step by step we reduce the pressure and the strain on the bond pad. You can see such a bond on the bottom right hand side. This is what it looks like under a 20 kilovolt electron microscope. Now the next step is to form the actual loop. And when I started doing that, I thought, well, what should go wrong forming the loop? Actually, it's one of the, as I figured out, one of the more critical processes about wire bonding, actually, because if you move the head into a wrong direction, you will just tear off your bond. You will just crack your bonding point. So the capillary ascends, and since the wire is guided by this airflow in the tubing, we open the clamp and just pull the wedge in a predefined manner that puts the least amount of stress onto our wire. And depending on what you want to bond on, like how thick is your chip, and so on and so forth. Or as you can see here, for example, maybe you want to bond like 3 rows of wires interleaved. You have to approach this with different loop forms, which can be quite a hassle to figure out what you're actually doing there. So the first time I wanted to bond a chip to a PCB, just the process of figuring out the correct loop form, not to break the wire, took, I don't know, at least 6 hours until I could do that repeatedly. So the loop geometry is not as easy as it looks like. So after forming the loop, we start all over again. We do the same process with the second bond, and then comes the tear-off phase. The tear-off is basically what it sounds like. We close the clamp and we just tear off the wire. But also for tearing off the wire, we want to do it in the correct angle. We want to do it with the correct momentum. We want to do it with the correct force. And we want to wait a specific time after doing the second bond. Because if you, and I'm going back to this picture, so you see this little tail on the left side of the wire. So after tearing off, after the second bond, we still want to have that tail in our bonding wedge, because if we tear off in the wrong way and we lose this tail, we can stop our process, especially if it's completely automated. We can stop the process and have to make sure that the wire is guided through the wedge again perfectly, that we have wire underneath the wedge to bond on the next pad. So, sounds quite straightforward, right? Well, there are 3 major errors that typically occurred when I tried bonding. One was the non-stick on pad failure. So this non-stick on pad failure is basically happening when the wire doesn't stick to the surface at all, which is usually a sign of not working cleanly enough, or having too little force or too low ultrasonic. But yeah, I figured out that it mostly correlates with me cleaning the chip properly, or the time I spend between cleaning it with, for example, isopropanol or alcohol for that matter, and starting the bonding process. And yeah, okay, of course, effects. It's an open circuit. There's no electrical connection. You can't use that bond. The second one is, well, a bond lift. When we see a bond lift, the bond usually attaches to the pad. But when we want to run the loop, or when we want to do the tear off, we also detach the bond from our substrate again. And well, if the bond really attaches to the surface, it usually doesn't have to do that much with contamination, because it already bonded, so we got through the oxide layer. But maybe the bond time was too short. Maybe we pushed the wire down not long enough. And the third thing, so if you overdo it, then if you overcorrect, what you get is a cratering damage, or a pad damage, which basically means that you scrub away all of the pad metallization, which happens quite quickly, actually. So, I mean, I think I did everything wrong with those machines that I could do wrong without breaking them. And no, I don't think I did everything wrong. I think there are a lot of things that I can still do wrong, and I will do wrong in the future. But yeah, this cratering is also super annoying because sometimes you really scrub away the whole pad, and then also the bond doesn't really really attach. So you have a few parameters to really tune to your specific chip. You can't just take any chip, any PCB, sit down, and then bond. Oh, I've got a different chip. I've got a different PCB. Let's just sit down, take the same parameters, and do that again. So it's always a really tedious process. One of the parameters that I already mentioned is basically the bond force. The bond force is just the shear force that the wedge applies to the wire while it is pushing the wire and while it is moving the wire. So if it's too low, the bond usually doesn't stick. If it's too high, you will get this cratering and pad damage. The ultrasonic vibration or the ultrasonic power. Well, the ultrasonic power provides this localized scrubbing, and the amplitude determines how much oxide you push away, how much you disrupt the oxide. And also there, if you put too little power on it, it doesn't stick to the pad. If you put too much on it, you will get this. You will get a very, very squished down bond, and the wire coming out at just a very tiny edge, so it breaks off quite easily. Third thing is bond time. So I played a lot around with the bond time, and I figured out that was actually the parameter that was had a huge impact on how well I could bond. Especially when it comes to the bond lifting, right? So under the microscope, you saw on the picture of the machine maybe that there is a microscope attached right to the bonding machine. You can easily look through that and observe the bonding process. So it looks like everything is bonded correctly, and then it moves up, but it still pulls off the bond. But on the other hand, if you overdo it with the bond time, you also get a pad damage. Okay, surface cleanliness. Let's not talk about how clean I'm working. But there's I don't think that there's too much cleanliness that you can put into this process. So now let's go into the interface. How do you set that up? Well, I said it's a regular CNC machine, but if someone has contacts to FK Delvotech, please tell them that it's a pain to use their machines, and I really don't understand why it is so hard to give an SSH interface to a machine that costs like almost 200,000 euros. So for all of the bonding parameters, you always have to go into this graphical user interface. You have a tiny trackball, and then you go around and click in it, and then you type. And okay, so you can save the configurations, right? You can save the configurations. You can save them on the machine, but you also can't copy them via SCP or whatever to another machine. You have to unscrew something to put in a USB stick, and then actually go into an administrative menu to then copy the files. It's I don't know why they did that. So I'm hoping for some people at some point to release an open source version of that software. Well, when we're looking at this interface, on the left hand side you can see a picture from a camera that sits in the bond head, right? And we Okay, you can maybe see this little red ellipsoid that's here. That is basically the cursor that you're moving. You adjust the X, Y, and the Z coordinate where you want to bond. You can adjust the time, the power, the force, and whether the clamp is open or not. Obviously, you have to do that for both bonds. And when you program such a machine, you basically sit there with this trackball. You move the bond head until you're over the pad, and then you just start trace and do this and do that and adjust the height, and then you go over to the other one, and then you do that again. It's a really annoying process, and it takes so much time. But if you put in the time and do it correctly, it usually also works quite well. When you're done selecting the points that you want to bond, well, you have a lot of bonding power and force and delay parameters and how you want to control the ultrasonic power and all of that. I played around with that a little bit. I haven't gone through all. I have not iterated through all of those things yet. Maybe I'll do that in the future. And then the loop parameters. Okay, so the loop, in the beginning I thought, well, the loop, that must be easy. It's just moving up and moving somewhere. But also for the loops, you can, in this machine, you can basically program all of those waypoints. You can also add arbitrary waypoints for the bond head to move in a specific way. And that's absolutely necessary also when you're trying to bond like multi-level chips, or you want to bond interleaved to really adjust the wires. In the end, the wire is, well, still flexible, of course, right? So you're not actually pushing and pulling the wire while the loop is formed, but it still follows a little bit the form that you, or the trajectory that you moved with the bond head. Well, tail parameters, not that interesting. And if you set that up all correctly, then you might get to a point where it looks something like this. Isn't that satisfying? That looks fine. So, what I wanted to tell... What I wanted to tell you with those last 9 steps and all the interfaces is, well, it looks quite easy to set that one bond, but it's a super annoying process. It's also a fun process when it works, but I mean, we're electrical engineers, sort of, all of us, right? So we all have a high tolerance for frustration, probably. Yeah, and if you do it really correct, then hopefully it looks something like this. Right here, you can see through the microscope the bonding on the pads. You can also come to the front later and look at the real thing. Well, that's actually one that I screwed up, so I brought that. I didn't bring the ones that are working properly. Yeah, this is what it looks like when you just start doing it. Yeah, that it's not hard to see that the bonds all have different heights and different widths, and they are really, really out of place. This is not what it should look like, but it still worked. So the connections worked. It didn't work for long though. Well, what is my resume for that? Well, hardware is hard. We all figured that out. And it was totally fascinating to me when I looked into older books that in the 1960s, like people like Jack Kilby and those, they actually did that by hand. So they had sort of soldering irons with ultrasonic transducers and did that with tweezers and this ultrasonic transducer under a microscope. Obviously, they didn't have 100 micron pads then, but that was quite interesting to me. Well, what else would you imagine, right? There is not a machine for that in the beginning. Well, then it somehow became big tech industry, and I'm actually wondering. That's why I made this 3D printer comparison in the beginning. How far we are away from basically building something like that in an open source way, in an accessible way. Because yes, today it's still 150K, but I don't think it will take too long until maybe where are Alex and what was his name from this morning? Until you guys also build your own open wire bonding stuff. I would love to see that. So, I mean, this is it's a little bit out of place here because it's not open PCB design, but I just wanted to maybe open your eyes a little bit that there is also something out there which is open source chip design. Some of you probably have know Matthew. He's very, very active in that open chip design scene. We also ran a conference here in Bochum. First time 2021 open tape out. So if you're interested in that, please talk to me or talk to Matthew. And if you want to buy such a wonderful shirt on the right hand side, full stack starts with tape out. I had this discussion like a couple of years ago with this one guy who told me he was a full stack engineer, and I didn't really know what a full stack engineer was, and I was completely excited, and so you're doing everything? It's like, yes, I'm doing everything. So I go, okay, go through the process with me. Well, I go on this website and then I book a VM and then I click, I want to install Debian, and then I set up. Okay, no, full stack means something else, and I look forward to a future where we actually have a complete open source full stack. What do I do if I don't, when I don't bond wires? Well, I'm basically mostly invested in building monitoring systems, either for ultrasonic, we build compute modules, or tiny oscilloscopes like that. So if you're interested in having a Python scriptable oscilloscope that can be synchronized over multiple channels by using the USB microstarter frame, you can get one from me. We do that for all kinds of industries, like whether it's plastics, plastic injection molding, physical experiments, automotive, biochemistry, or mining equipment. My name is Stephan Bökelmann. I didn't say that in the beginning. And I usually organize those conferences. I organize trainings. If you want to, you can have a look at my tutorials. Looking at github.com/stemgraph, there's a bunch of really easy to follow tutorials for beginners to get into programming. I'm teaching at the Technical University of Bochum, so I prepared all of those things for first and second semester students. So if anybody of you has to onboard somebody at work, maybe take a look into my tutorials. And if you find a bug, please fork and make a pull request. And besides of that, I develop monitoring systems together with Tabea and Odin that you probably have also met or seen at one point. Thank you very much. And I'm going to say this was 44 minutes and 7 seconds, so I'm very proud that I actually found the right spot.
Uh-oh. first impression.
Oh no, but this is not an oral exam, right?
What requirements do you have on the PCB for bonding? What is the surface finish?
Inic.
Best.
Just regular inic.
Just to copper, or has it to be gold plated? Or?
Well, I've tried it with different surfaces, and up until now, I have not yet figured out any problem with any surface finish. So the usual problems that I'm getting are more on the chip side, because the only as far as I can tell, which is probably absolutely wrong, but the only problem that you really get when you're bonding onto the PCB side is that you apply the bond force for too long, and then you press down the bond too much, and at some point the wire breaks off the bond. So there's no weird thing that I'd really need.
Can you say your GitHub site again, please?
The GitHub
site, you said it before?
It's there, STEM graph, STEM graph. So when you look into those files, you will also. Well, I'm not completely done doing that, but actually I want to render a graph from my tutorials that you can fill out a form, what you already know, and you can fill out a form where you want to go, and then it gives you a trajectory through this network. So when you look into the actual repository, you will see a lot of UIDs, basically. And if you look at the raw MD file, I should see that here, you will see that it all comes with a meta information block, and it has an JSON array that is called depends on. So I basically encode for each tutorial what it depends on, and then I parse it and render a graph from that.
So I have a question about contaminations that you deal with on the wire bonding pads. So in the past, I've gotten devices out of the clean room, and my wire bond pads were covered in aluminum oxide.
Mm-hmm.
So how do you go about removing that oxide? Because you can imagine it can become very thick when, for example, they made some mistakes during fabrication processing in the clean room?
That's a good question. I have not had a problem with an oxide layer that was so thick that my bonds wouldn't work eventually if I set the correct parameters. So we're just cleaning it with isoprop, and then I'm bonding on it. But I have to say, that's why it's called a poor man's intro, right? I'm so far away from being an expert, and people. I'm just saying that once again. Do not follow my advice on anything. That would be a really bad idea. Yeah, so I can't really comment on that because I haven't had that problem yet.
Right.
What kind of ICs do you need that you have to buy a 150K wire bonder? That you depend so much on like an IC that cannot be found in a normal package?
I'm bonding our own, not my own ASICs, but ASICs from our larger work group. So I'm working as a researcher in the experimental Hadron physics department, and what you saw is a anti-proton pixel matrix sensor, so-called a high voltage monolithic active pixel sensor. It's basically a reversely biased diode that has a thick recombination zone, and when an ionizing particle runs through that diode, there is a charge that runs over a charge-sensitive preamplifier, a shaper, and then some digital readout electronics that, or let's say timers that put 2 timestamps into a RAM cell, and then we sort of SPI that out of that. So yeah, it's not a chip that you could just buy off Mauser. It would be great though.
When you're gluing the chip to the substrate, how do you apply the glue so that the layer thickness is uniform and also that the chip sits flush with the surface?
Yes, thank you very much. Next question, please. Well, currently I'm using a acupuncture needle, and I'm taking a really teeny tiny bit of araldite glue, and I'm applying it carefully. Look at it under a microscope that it appears to be the same thickness everywhere, and then I just position it with tweezers or with this what's it called, with a vacuum pump under a microscope. I wiggle it a little bit around and hope that it sits flat. But as I said, well, the wire bonder itself, I do calibrate the height, but there is still a sensor that measures the resistance of the chip. So yeah, I think I could do better with everything I'm doing.
Have you ever figured out if you connect the bond wire to the gold or to the nickel layer, or is it a compound of all 3 metals? So the aluminum, the gold, and the nickel.
Have I figured that out? Well, I have not. Ground it down and looked at it under an electron microscope, so I have no way of knowing right now.
Yeah. And do you know if there are some bonding processes available which use an active gas like hydrogen or carbon monoxide to prepare the surfaces?
No, I don't know. I only know that there are a lot of processes in which you use nitrogen, basically as just the exact opposite, right? Because you want to have it inactive. But I don't know. Maybe somebody else. As I said, I'm not. No, I don't know. No.
Okay, thank you, Stephan.